Good morning, good afternoon, and good evening, everyone. Thank you for joining us on virtual session number 2, Weather Systems, for the VFS workshop on eVTOL infrastructure. Just a couple of minor things to start with here, logistical. First off, questions will be handled at the end of the presentations. So if you have questions, please enter them in the questions box in your control panel, and we'll capture those. And what questions we can get to during the session, we will have answered then, and we'll capture all of the questions and post answers on the website in the near future, within a couple of days or so. The chat room is open, so feel free to send chats. We'll be monitoring that as well. We appreciate everyone joining in today, and we expect a really good discussion. We had over 400 registered to attend. So welcome everyone to virtual session number 2 for the eVTOL workshop infrastructure on weather systems. I'm Jim Sherman. I'll be your host for today. We have on the line with us Rex Alexander, our moderator, as well as Stephanie Avey from NOAA, and Matthias Steiner from NCAR, Don Berchoff from TruWeather, and Marilyn Pearson from the FAA. We'll get started here in just a second. I want to give a little bit of background on VFS for those that are not familiar. So first I want to thank our sponsors for our eVTOL workshop, Gannett Fleming, Deloitte, Uber, and PSNS. Especially today, Deloitte has graciously accepted to sponsor this session, and I see that we have a few Deloitte folks on the line. So thank you very much for your continued support. Vertical Flight Society has been around since 1943. We were formed as American Helicopter Society. We cover everything vertical flight, from helicopters, eVTOLs, and some STOVL. Our mission is to advance the vertical flight industry and promote safety throughout the industry. So we've taken eVTOL on from the beginning, and we have been advocating for it ever since. Our role runs from industry to academia to government, and we tackle these tough challenges to try to promote the industry. As I said, we've been around for 75 years. We've had some pretty good accomplishments over those 75 years, including helping to establish the NASA Army Joint Office, National Rotorcraft Technology Center, and a few other things. We've also supported major transformative programs such as the Joint Strike Fighter and the V-22 tilt rotor. And we continue to support new programs for helicopters, as well as hybrid and electric eVTOL. So we are really pushing to improve this industry and making sure that it's safe and functional. For those of you that are not aware, we also operate the eVTOL.news website. It's more of an encyclopedia of everything eVTOL. We have an aircraft directory which has cataloged over 260 aircraft in 5 different categories. We maintain as many articles on eVTOL as we can find, put them there, with timelines, maps, company directory, and educational videos available there. And you can sign up for our bi-weekly newsletter, which covers everything in the industry, from infrastructure to vehicles to government activities to regulatory, everything that you can think of. And it's not just in the US, it's a global collection. We also have a number of other activities that we've captured. So we have our Facebook page, and there's a electric VTOL portion to that, as well as Twitter, YouTube, Instagram, and Vimeo, where we've collected a lot of our courses as well as presentations on eVTOL. And of course, we have just a number of different things that you can go out and educate yourself on eVTOL in particular. So with that, I will now turn it over to our moderator for today, Mr. Rex Alexander, who is a consultant for the Vertical Flight Society on infrastructure and is very instrumental in helping us organize these workshops. And with that, I will turn it over to Rex.
Thank you, Jim, and thank you to everyone who has joined us today for what is expected to be a fantastic session in our Urban Air Mobility Infrastructure webinar series. Today's series will focus on weather systems as they apply to urban air mobility. My name is Rex Alexander, and I am the Vertical Flight Society Infrastructure Advisor and today's moderator. We have 4 exceptional weather and meteorological experts lined up for you today, and we are sure that you will enjoy what they have to say. With that, our first speaker today is Stephanie Avey. Stephanie is a techniques development meteorologist with the National Weather Service, working at the Aviation Weather Center in Kansas City. She currently works under the Aviation Support Branch, focusing on research to operations through aviation weather testbed. She joined the Aviation Weather Center in 2017 and is involved with several aviation weather testbed projects with a focus on ceiling and visibility. She also serves as the project lead for enhancements to Helicopter Emergency Medical Services, or HEMS, weather tool. So please welcome Miss Stephanie Avey.
Thank you, Rex, and thank you to Jim for inviting me to be a part of this panel today. Yes, perfect. So Rex, you did a fantastic job introducing me, so I won't dwell on that any longer. Like you said, I work at the Aviation Weather Center, and I'm going to give a brief overview today on how we evolve our products at AWC to meet not only the current needs of our users, but also look to provide for the future users as well. And so for those that aren't maybe familiar with the Aviation Weather Center, we are one of 9 national centers within the National Weather Service as part of NOAA. Our key goal is to be the trusted authority and leading innovator for aviation weather information. And we're located in Kansas City, Missouri. We provide domestic and international aviation forecasts and warnings. And one of the key ways that we disseminate this information to our customers and to the public is through our website. And you can find that at www.aviationweather.gov. And as part of the Aviation Weather Center, we have our Aviation Weather Testbed, and this exists as both a physical space within our building, but it also encompasses our entire research to operations framework. And so when we are developing new ideas and taking new concepts and thinking of how we can bridge them into an operational setting and framework, we run everything through this process through our testbed. A big key component of that is actually having stakeholders and collaborators into our testbed, the actual physical portion of it, every year for our annual experiment. Typically, this takes place the 2nd, 3rd week of August. Unfortunately, it doesn't look like that's going to happen this year, but it's a really fun event. We bring in multiple different stakeholders, just as an example with all the logos there at the bottom of this slide. And what this allows us to do is to get these products, these new ideas in front of these users. It's in front of our meteorologists within the Weather Service. It's in front of model developers who are helping provide that information, as well as the users of these products as well. And so this is a really key component of figuring out, are we ready to move this into operations, or does it need a little bit more work? And one way that we can facilitate getting this user information, getting this very valuable input, is working with our friends out at the Tech Center in New Jersey, the Aviation Weather Demonstration and Evaluation Services Group, or AWDE. And their goal is to explore, integrate, and evaluate next-gen aviation weather concepts. And so they work with us quite a bit. They also work with other FAA entities out at the Tech Center, in addition to outside partners as well. And one of the key components they can provide for us is that human factors expertise, and really gaining, engaging with the user, how they're interpreting the different products and information that we're trying to provide for them. And so at AWC, we've been collaborating with them for several years. Most recently, our focus has been on assessing the utility and usability of some of our web products on our website. And we've done this by having evaluations with our users, having them help us facilitate those. And then we've also had them help do in-person interviews with our users as well. So they have a nice little lab out there at the tech center where they can bring users in and they can sit them down and sort of simulate the environment that they would be in with the same computer systems, etc. And then get that one-on-one interview sort of back and forth repertoire with them to get that feedback that we're really, it's really valuable for us and how we evolve our products moving forward. And sort of three of the main products that we've been collaborating with them to evaluate most recently has been one of them, the HEMS tool, and I'll speak to that in just a moment here. Also our graphical forecast for aviation tool, or GFA. And then we've also had them look at how users interpret probabilistic ceiling and visibility information, as well as we sort of move towards forecasting and then a probabilistic framework. So that kind of gives you just a very brief overview of how we at AWC, how we're taking new ideas and concepts and getting user input in hopes of getting those new ideas into an operational setting. And now I kind of want to switch gears a little bit and talk about, what products do we have at AWC right now that can provide this weather information at low altitudes to serve, the UAS community, the UAM community, those users. And so our key tool, and I kind of teased it just a couple slides ago, is our HEMS tool, our Helicopter Emergency Medical Services tool. And we've worked very closely with Rex Alexander in years previously to ensure this tool is being used by that community. And if you're not familiar with it yet, it is a web interface on our website, which is designed to show weather conditions for short distance and low altitude flights that are common for this HEMS community. And the idea here is that we're presenting this information in a format that they can understand and interpret very quickly and in an effective manner, so they can decide if it's safe to fly or not. And this is just an example of a screenshot of what that looks like there on the right. And it has, a plethora of information that's important for low-level flyers. We know in particular that this community is very sensitive to changes in cloud ceiling and surface visibility. And so something unique that the HEMS tool offers is a CNV analysis product. And if you're not familiar with what an analysis is, it's basically an interpolation between observational data points that give you a guess as to what the current conditions are right there when you don't have an observation. And this is really important for these flyers because they're taking off and landing in areas that don't necessarily have a METAR observation or a TAF forecast. And so we've focused over the last few years on how we can enhance the CNV capabilities within the HEMS tool. And we just had a pretty major update to our HEMS tool at the end of March, actually. March 31st, we released it. It was the first update we've done to the tool since we operationally implemented it back in 2015. And this was a multi-year effort. It was in collaboration with the FAA's Aviation Weather Research Program. It was funded by them. We also worked with our other NOAA partners in terms of the model developers and the quality assessment team to look at the different products we were looking at. And the main goal for this work was to see if we could enhance the CNV capabilities by providing better product for our customers. And what we ended up moving forward with is a new ceiling and visibility analysis, and we also included a forecast, an hourly forecast of CNV. And this is something that we weren't previously offering to users of the HEMS tool. So it's a pretty big deal for us, and we're pretty excited about those changes. And in addition to the main goal of improving the CNV capabilities, we also made some improvements to our user interface, make it a little bit more user-friendly, user-intuitive as well. So that's where we're currently at with this HEMS tool product. But of course, we're always trying to think what's next, where are we going from here, and how can we evolve this product for the future? And to do that, we have to ask ourselves, who else is using the HEMS tool? And we know while it was designed for the HEMS community in particular, thanks to Rex, we know that several other low-level flyers are actually using the tool as well. This is just an example. We've got hot air balloon flyer operators, hang gliders, crop dusters, and of course, drone operators are starting to look at this product. And so when we think about this community and how we can serve their needs, right now at AWC, we're supporting FAA-regulated manned aircraft. So we're talking flights above 500 feet for the most part. And we know that we're not meeting, our products don't currently meet the needs of the UAS or UAM community. And in order to do this, we'd really have to focus on that information below 500 feet. That would include higher resolution winds and additional observation data sets, especially in those really dense urban environments. And so while we may not be meeting those needs yet, we're always looking for ways that we can provide some useful information in a framework that we may already have established. And so we're starting to bridge that gap. We're starting to think forward on this. And one product that we do have that's used quite a bit by our customers is our graphical forecast for aviation, or our GFA. And this product, it's designed for the general aviation user, but it has a lot of capabilities and a lot of user interface capabilities that our users of the HEMS tool have actually asked for. And so there's this idea that we can integrate our HEMS tool into the GFA, make it sort of a seamless product. And that would be our GFA low altitude, or the GFA LA. It maybe doesn't roll off the tongue as nicely as HEMS, but I think we can work on that. The idea here is that we're going to maintain and provide the products that the low altitude flyers need, but we're going to give them the look and the feel and the capabilities that we provide in the GFA. And this includes things like higher resolution winds below 1,000 feet. That's not something that you can currently get from the HEMS tool itself. This also provides a lot more forecast information. The GFA is kind of geared towards general aviation flight planning in the short term. And so there's a lot more forecast information in there that could be valuable to low-level flyers as well, like cloud layer information and precip and weather forecasts from the National Weather Service. We can provide turbulence information and low-level wind shear. That's something that we're constantly being asked for by this community. And then we're currently working, this is a funded project by the Aviation Weather Research Program with the FAA, to look at adding additional observation data sets from the MATIS data set. So this would allow us to provide additional station information beyond just the certified ASOS stations that we currently provide. And in addition to sort of bridging these two products, we're also looking to give our website a whole new look, and providing more consistency across our products as well. So this just kind of gives you an example of this more modern look that we're going for, more user intuitive, and most importantly, more mobile friendly as well. This is a huge ask that we get is, hey, can you guys give us a mobile app, or do you have a mobile app or something that we can pull up on my phone? And we hear that, the HEMS tool maybe isn't so great on the mobile side of things. So we really want to be able to provide that. At this point, we can't provide an app per se, but we can make our website more user-friendly on a mobile platform. And so on the right, you kind of get an example of what this new interface could look like on a tablet or on a cell phone. Just, a lot more user intuitive and just easier to visualize on your phone. So instead of having to pull it up on the laptop before you head out, you can actually pull it up on your phone when you're out in the field, flying your drone, or before you hop into the cockpit as well. So that kind of gives you an idea of our 5-year plan, so to speak. But like I said, we're always trying to think forward and where are we going next? And we know that technology is advancing with urban air mobility and the future of what that could look like. So we're starting to wrap our head around this and how can we provide for this community as well? And right now, there's no standard from the FAA on where these operators should be getting their weather information. So without that requirement from the FAA, we're not able to provide that information. We don't specifically provide that information for them. This will allow us to, once we have a requirement from the FAA, this will allow us to bring in more funding. Funding will be a huge component of this. We know that just having micro modeling within urban environments, et cetera, that's just going to take a lot more computing power that we don't currently have. In addition to computing, we also have to think about the observational data set that we're going to need to provide to these users. And on the left there, just an example of one idea would be to have these drones equipped with weather sensors. Of course, this would provide a huge high resolution observation data set, but being able to ingest that data and as well as disseminate that information to our customers, that's going to be something that's costly as well. And then, of course, just continuing to develop products and test them and ensure that we're putting the best product out there for our users. That's something that, we'll continue to develop as well. So we're not there yet, but we are always open-minded. We're trying to gather information from the community and from all of you here and how we can start to move forward in that direction. So with that, I will thank you for listening, and my email address is on there, so if you want to reach out with any other questions.
Thank you, Stephanie. We greatly appreciate you sharing with everyone the new technologies that NOAA and the Aviation Weather Center are working on for low-level flight environments. Very exciting, and looking forward to what wonderful things you guys can do in the future. So for our second speaker today, I would like to welcome Dr. Matthias Steiner. Dr. Steiner is a senior scientist with the National Center for Atmospheric Research, serving as director for the Aviation Applications Program of the Research Applications Laboratory. Dr. Steiner leads new initiatives and directs research and development efforts broadly aimed at mitigation of avoidable weather impacts on various sectors, with a particular focus on aviation. At present, Dr. Steiner is leading efforts to understand weather sensitivities and requirements for the rapidly growing interest in urban air mobility, and using unmanned aerial systems for wide-ranging applications and safe integration into the national airspace system. Dr. Steiner has received multiple recognitions for excellence, contributions to field programs, scientific missions, and outstanding publications. Most notably, Dr. Steiner is a fellow of both the Royal and American Meteorological Societies. Please welcome Dr. Matthias Steiner.
Thank you, Rex, for the introduction, and also thank you to the Vertical Flight Society for inviting me to participate in this webinar on weather systems. So my talk, what I will be touching base on is really focusing on the weather challenges, particularly in the urban environments. And there is obviously a lot of different weather aspects that we are familiar with, and I can't talk about all of them. So I really want to focus on the winds in particular. So from an operator perspective, you have clearly the ground operations aspect on the vertiports, and where you service the aircraft, you transfer passengers or cargo onto the aircraft, and you're exposed to the elements because you do that outside. So you have to deal with thunderstorm impacts, lightning, heavy precipitation, or if it gets cold with wintry aspects like snowfall or icing conditions. Very extreme temperatures, very hot or cold, can obviously affect your battery performance, which is of concern. And then we have winds, which may blow things around and affect you in various ways on your platform where you're trying to operate. Then once you take off and get into the air, you are still exposed to the same kind of weather elements, but they affect your operations in a different way. Clearly, takeoff and departure, or the approach and landing on rooftops may be challenging because of weather impacts. The transition from vertical to horizontal flight may be a particularly sensitive part of the flight operation. And then en route, you want to avoid, weather impacts, particularly strong winds and turbulence that can affect your ride comfort from a passenger perspective, or also your battery consumption if you have strong headwinds or need to use your control surfaces quite a bit. It will drain your battery power much more significantly than you might have expected Another often overlooked aspect in terms of weather impact is the noise generation and how noise propagates. That clearly is affected by the weather conditions. So let's look at a particular environment and just start thinking a little bit about what aspects play into this. And I'm using here Los Angeles as an example just because it is one of the major places that is being considered for urban air mobility demonstrations for early adoption. And I'm just highlighting 3 locations here: the airport LAX, which you see here along the coastline, then the downtown LA area, which is depicted here with the high rises, and a more residential area here more to the east. And so you see different kind of infrastructure there. You see different kind of urban development. Residential areas are obviously much flatter in their construction than a downtown area with high rises. But the LA area has also significant mountainous terrain in the potential flight operations that I indicated here, just as a circle of about 50 miles. Obviously, there may be operations that go beyond that, but this is sort of a typical range that you would operate in. And so you have quite a range of aspects to deal with related to terrain, related to the urbanization and the built up infrastructure related to oceanic, like the water aspects, etc. So if we keep that in mind and look at 25 different locations around the United States, there's obviously different geographic influences that play a role here. The latitude clearly affects the solar radiation that you get in a climatic sense that drives your temperature and other things. You have major water bodies that provide local sources of moisture, which may influence what you're experiencing. Mountains, it's obviously the range of altitude that you may have to deal with affects your operations. The air density plays into this. If you have to go to much higher altitudes, the air gets thinner, and therefore it affects the performance of your aircraft. The land cover gradients in general affect the differential heating, like water surfaces and land surfaces are heating up differently throughout the day, and I get into that a little more later on. But also it could be just different surfaces, whether it's forested or agricultural land, could create differences in local circulations. So what you see here on the right is just for these 25 cities ordered by the fraction of water in the domain. Clearly, Miami shows up at the right here with the most water surrounding this area. And in all the coastal cities like LA, Boston, Jacksonville, Chicago, San Francisco, New York, etc. And as you go over to the other side, Phoenix is a pretty dry area where there's maybe a few smaller lakes, but not really much water. If you look at the elevation range in contrast, then you see that Seattle, Las Vegas, Portland, Los Angeles, Denver, Salt Lake City have significant altitude ranges where you go from sea level up to exceeding 3,000 meter or maybe even approaching 4,000 meter in elevation changes. And this is substantial. So you have to consider that from an aircraft performance perspective, but not just from that in terms of how the aircraft may behave. It may also affect the weather aspects that you see there. There's obviously also dynamic elements from weather systems, clouds and precipitation that may affect an area. You have winds that play into this. And then obviously you have the city, the urban landscape that creates particular wind aspects and challenges there. So as I said, winds play a significant role in this area, and I really want to focus in on this there are different kinds of wind systems that we need to appreciate. And I touched on this a little bit already. There are thermally driven wind systems that are, driving based on the differential heating from land surfaces. So if you're in a coastal area, the water surface and the land surface are heating differently throughout the day. During the daytime heating, the land heats up more quickly than the water surface, and therefore you start seeing a sea breeze, winds coming in at low level from the ocean onto the land. And at nighttime, you have then the reverse happening, where the water doesn't cool as quickly as the land surface, and therefore you end up with a land breeze, and that reverses the flow. And when you think in terms of Florida, you may actually have sea breezes coming in from both sides, and where they are colliding somewhere in the middle, you're really starting to kick off thunderstorms that then produce heavy rainfall and lightning and other things. Then you have different kinds of pressure system. Anyway, so let me continue the story while Jim is setting it up. In terms of pressure system, I talked about the strong downslope winds that you may see in the California area, the Santa Ana winds. They can produce pretty strong winds. And then we have also thunderstorms that can also produce outflows that actually can travel substantial distances away from the parent thunderstorm that produced them, and I'm talking tens of kilometers away. So you may be significantly away from a thunderstorm, you think you're safe, but you may be possibly surprised by a low-level gust front that may surprise you in that. And then ultimately, getting into the urban landscape is clearly giving a lot of additional issues from a wind perspective, because you have channeling of winds going through the urban landscape, and the buildings themselves can actually create significant turbulence, the vortex shedding off the buildings, and that turbulence is also depending on the situation of a particular time of day. So I'm going to slide 5 here. This is, I'm clicking quickly through. That's essentially the various winds that I talked about without graphics. Obviously, people have, developed textbooks written about those different kind of things. So I don't have obviously time to get into this. It's kind of just a reminder that there is a lot of things going on in the lower parts of the atmosphere from a dynamic perspective, wind perspective, that can affect your operations. So now let's take a look at the various cities. You see them in the upper right here, the 25 cities that we looked at, the metropolitan areas across the United States, including Hawaii, to look at various weather aspects. And so what the plot shows down here is the cities ordered by sustained wind speeds, the frequency of sustained wind speeds exceeding 20 knots. And these are the blue purplishy bars here. And you see San Francisco shows up at the top, followed by New York, Denver, Boston, Dallas, etc., etc. But the sustained winds may only tell you part of the story, because there are gusts that you may have to be concerned too. So if you look at the gusts, which are the gusts exceeding 20 knots, the frequency of that, then you look at the red bars, and here suddenly you see that Boston is showing up as the top spot, followed by New York, and then Honolulu, and Chicago shows finally up near the top as the windy city. We know Chicago. So it's really, what matters? Is it the sustained winds, or is it the gusts that you're interested in? And these are just based on the ASO stations, essentially the METAR information that you're getting from those stations that are placed at the major airport. So what is the spatial variance across a metropolitan area? And then once you dive into the urban area, the cityscape, it becomes even more challenging, as I will show you in the next few slides here. So this is again the example of the Los Angeles area that I have shown you before. I'm looking here at windroses. Windroses, as you see here in the upper right, this is a way to characterize in a climatological sense where the winds are coming from, which direction, how strong they are, and the further the bar reaches into a certain direction, that means it's more frequently coming from direction. And then the color shading is the different magnitude of the wind speed. So this is kind of the generic plot. And if you look at these individual plots, for example, here, Los Angeles, these are these individual plots here, but now done on a seasonal basis, where on a monthly basis. So you see here January, February, March, April, May, and so on throughout the whole year. And it's beyond the point to explain all these graphics for each location, but the point here is to show you how different they are and that each location has their own footprint in terms of what the wind speeds are, where they're coming from, and how intense they are. For example, if you look here up in the Lancaster area, you get much stronger winds. If it gets into the reddish, that means these are winds that are exceeding 20 knots, etc. So again, it's the spatial variance that you have to be aware of as you operate in this domain. And that's true for every city, and every city is different. Now let's look at it in a different way, still with LA, but what I'm showing here, and that may be a little easier to comprehend. These plots, even though there's a lot of information, it shows here the seasonal cycle on the vertical axis on the top corner here, starting with January going down to December. And in the horizontal axis, it's the diurnal cycle, essentially the time of day. And looking at this plot, it really shows you the frequency of exceeding a certain wind speed. And in this particular case, I'm using a threshold of 10 knots. So what you see here for Los Angeles is that clearly in the afternoon hours, you have a very high likelihood of having winds that exceed 10 knots. Red is, up here, that's the color scale is 100%. So this is very typical for most of the year. You have stronger winds in the afternoon, and particularly in the spring through the fall, you have winds exceeding 10 knots. This is the norm. And then at nighttime, it calms down. Now, if you go a little over here to Fullerton, it looks like winds are really not a big issue. You still kind of see the afternoon enhanced winds, but it's not such a big deal. If you go up to Lancaster, it becomes a big deal again. You clearly have in the afternoon and throughout the night, you have enhanced wind speeds there, or likelihood of stronger winds. So all these locations vary in their footprint, how it looks. Now, if you look at the gusts, this is now on slide 9, is showing you the frequency of gusts to occur. And again, Lancaster here up in the northern parts of the domain that you may operate in LA area shows clearly a high frequency of gusts in the afternoon and into the evening hours. Much less so in Los Angeles at the airport area. Again, over here, China may have some gusts frequency in the afternoon. So, I mean, you could spend a lot of time looking at these highly digested information and how it varies throughout your operational domain. And you should be aware of that as you start planning to operate in there as to what you may be experiencing. So I mentioned the urban as a particular challenge. Prediction challenge, because it's a very dynamic environment within and above the cityscape, the built-up environment. It shows significant diurnal and seasonal variability. You have these vortices shedding off the buildings. You have flow channeling in the street canyons. And so we have been developing simulation modeling capabilities to really go down to building resolving scales. That means to meter scales to resolve that and understand what's happening in there. And so this is an example from Dallas, Texas, that I'm showing here some results What you're looking at here in the upper right of the graphic is a urban landscape that we built up based on LiDAR information from footprints and building heights to create this detailed urban landscape, to embed that in our modeling capabilities such that we can create a natural environment and understand what's happening. Just for scale comparison, this is about the scale of what you get from a high resolution rapid refresh pixel, a 3-kilometer resolution, which the best currently operational weather prediction model we have available from the National Weather Service. So this, what we are looking at now here, is all subgrid scale. This is processes that the HRRD, the high resolution rapid refresh, cannot resolve. So we have developed capabilities that are really making use of GPU, the graphical processing unit, to accelerate the processing such that we can do that in near real time actually by now. So what I'm showing you here are simulations for a typical January day here in the upper part, a typical July day here in the lower part, and how things progress throughout the day. So this is early morning hours, 6 o'clock in the morning, noontime, and then afternoon towards the evening. And each profile here, this is wind profiles, and it's only showing the lowest 1 kilometer above ground. So this is really in the boundary layer, the lowest parts. So if you can see that, you see the sort of a center profile with red dots. This is what you would get from a HRRD prediction in this situation. And the gray shading, these are all pixels throughout the domain, information that the model can create. And what you clearly see is quite the spread of the information. So you have much smaller wind speed and you have much larger wind speeds within that domain than what a HRRD profile would give you. And for comparison, we are also included here with the dashed line here. This is the top of the highest building in the Dallas downtown area, and that building is about 280 meters tall. So you clearly see the contrast here in the wintertime, January. You see a little bit of the vertical mixing happening in the daytime, but it's much stronger in the summertime, where you see clearly the vertical mixing and also the wide range of the wind speeds you see within there. We also looked at the turbulence of how turbulent is it in this environment, and here in this plot that shows on the lower left, I'm showing turbulence kinetic energy for a summertime July day, a typical day, and this upper row is for 6 o'clock in the morning day, a local time, and the lower row is for noontime. And then the column on the left is essentially about 30 meters above ground. The middle column is about 140 meters above ground, sort of halfway up to the top of the tallest building, and the right column is the top of the tallest building. And what you clearly see is the downstream that the turbulence created downstream of the buildings. You can also see how the wind may veer from the lower level as you go up with altitude. And you clearly see that at noontime, you see much stronger turbulence downstream of the buildings than early in the morning. In fact, if you look at this turbulence kinetic energy and you convert this into something like an eddy dissipation rate that the large transport aviation industry is very familiar with, and it's the EDR standard that ICAO has adopted. These levels of turbulence that you see in these simulations are actually substantial enough that large transport aircraft would avoid that. Large transport aircraft would avoid that. So imagine if you fly a smaller aircraft like a helicopter, or even smaller like an unmanned aerial system like a drone. You want to definitely be aware of where these things are happening, that you can stay out of it. So just to visualize more here, I'm showing you some animation to really visualize how dynamic this environment is. I hope you can see this animation here at the bottom. On the left side is a summertime midday convective boundary layer. On the right side is a more early morning stable boundary layer. And the plumes that you see here emanating up and out from the urban landscape, they are thresholded in terms of vertical motions exceeding 5 meters per second. That's pretty substantial. Green is up and purple is down. And in contrast, we had the threshold at a much lower level, about 0.5 meter per second in the early morning in order to visualize something. Clearly, it's much more stable situation here, not that much happening. But once the daytime heating starts and things are getting dynamic, turbulent, you see how clearing the urban landscape is not clearing you from the turbulence, from the vertical motion plumes that are emanated from the building, from the urban landscape. So you have to be aware of that. Now, also you see the richness of detail in these simulations, and the challenge is that we have limited observations to actually validate that, whether that is correct or not. We have done certainly a lot of effort in terms of validating with observations, wind tunnel studies, and specialized field experiments to appreciate how the fidelity of our modeling capabilities. And we are very satisfied at this point as to what the model is able to do. So I think there is pretty realism into these simulations that we can appreciate how dynamic this environment is. So let me wrap up here and also stand back a little more in terms of what are the key message points from a weather challenges perspective that you should be aware of. Clearly, weather affects the safety, efficiency, and reliability of aviation, and that includes urban air mobility. And the weather challenges are all the normal culprits that we are aware of from large and general aviation. But in addition to all of those, the urban landscape creates additional new hazards, significant wind and turbulence around the buildings and above the buildings that you need to be aware of. And ultimately, what is hazardous depends really on the type of vehicle that you're operating. And smaller vehicles tend to be more sensitive to these kind of weather impacts than larger ones. The observing infrastructure is doing a good job to capture things at the larger synoptic and mesoscale, what the weather phenomena are, but it's inadequate to capture the microscale weather that happens particularly in an urban environment, as I have shown you with some of these simulations. And urban microscale observing networks are really only slowly emerging. There may also be some networks out there that a city puts out there for maybe air quality monitoring or other things, but you may not have access to it. So there's a lot of opportunity to enhance the observing infrastructure, and not just opportunity, there is also need in order to provide guidance. In terms of analysis and forecast products, Stephanie already talked about this, what the Aviation Weather Center is doing in terms of providing guidance, but again, it's largely focused on large transport operations or general operations. It is still somewhat limited on the lower levels, the operations in complex landscapes. And while the HEMS tool is showing you weather information relative to the land surface in terms of altitude above ground level, which is terrific, but the information that is fed into the HEMS, there is opportunities there to get more micro weather input into that. And last point here, the current numerical weather prediction models clearly cannot resolve the scales of the processes that's happening in the urban landscape. Space and time resolution is too coarse. And again, this is a simulation down here. This is an example from Oklahoma City, a vertical cross section where you see again these plumes emanated from the urban landscape. And this is about this pixel from a single Hz pixel, the scale. So it really is not resolving what's happening at that scale. So I want to leave it with that. So thank you for attention.
Dr. Steiner, thank you so much. great in-depth discussion on the challenges that we're facing in the urban weather environment for sure. Our next and third speaker today is one only Don Berchoff. Don is co-founder and CEO of TruWeather Solutions. Don has deep expertise synthesizing complex weather data sets into simple decision insight for operators for unmanned autonomous systems, ground transportation, logistics industries, and the emergency management community. He is an Air Force veteran with 35 years experience in weather industry and logistics systems, including a year serving as the expeditionary base commander at Manas Air Base, Kyrgyzstan. He designed and led regional and global aviation weather operations centers, responsible for providing aviation weather services to over 200,000 Air Force and Army missions worldwide. A distinguished meteorologist and technologist, he led the National Weather Service Directorate for Science and Technology from 2008 to 2012. Please welcome Mr. Dan Berchoff.
Okay, thanks, Rex. Welcome, everyone, and thank you, Vertical Lift Society, for putting this on today. First of all, I'm awed by the work of the folks that talked in front of me today. As most of you know, the weather industry is a family, and we work these problems together. I'm now in the private sector. I was in the government for 28 years. I've had the pleasure of working with some of our great research institutions such as NCAR and Matthias, and working within the National Weather Service with the Aviation Weather Center. So I think it's important to understand that we are working this together and trying to figure out how do we bring the best outcomes to attack this problem. And so I think that's an important takeaway today. As an operator with an operator view of things, I'm going to take a little different approach to my presentation because I leave the expertise up to Matthias to figure out all the challenges and how to solve them scientifically. I will say that there's a couple of things I want to mention. Some folks may be asking why, I fly helicopters today in the city and, we don't have these big issues. And I say the answer to that is that's true. However, what we're talking about in the future is a high density operations environment based on very tight scheduling and moving people around. And when I think about this idea of urban air mobility and carrying people to the airport or to the train station and having them align with a driver on the ground or catching an airplane in JFK and being there on time and just in time, what we need is, the environment we work in today with the tools we have are just not going to be able to, really support that scalable business model that people have a vision for. And I think that's one of the important takeaways, because even the great work that Rex has done with the HEMS tool and working with the Aviation Weather Center, most of the data is going to have to be machine to machine shared in the future. We're not going to have necessarily pilots in every case watching the weather for every route for every mission. In the cases of small UAS, it could be flying many drones, many autonomous vehicles with just one person potentially sitting in an operations center and just watching for things that are not going well and mitigating and working through those. We're not going to have somebody that's going to be able to go through and sift their way through lots of data to figure out if they're going to have fog and stratus over Sheepshead Bay in Brooklyn when they're flying from downtown Manhattan to JFK. And it could be the only fog in that route is subgrid, as Matthias said, over Sheepshead Bay. So these are, the challenges that, I'm looking at as somebody who's looking at bringing a private sector approach to this, working with the government and working with the research community. So I think the first thing is weather impacts all our decisions. A lot of us, it's second nature. For experienced pilots, it's second nature. But there's a lot of folks out there today flying drones that don't have that experience that some of the pilots out there have in weather and understanding the atmosphere and some of the things Matthias talked about. It's important to have a context. And, when weather impacts our decisions, When we care about it is only when it actually impacts the application we're doing at the time and the place that we're trying to do it. And many times there's folks that think weather is just the price of doing business, it's something that, we can't control. But the truth is there's a lot of good data out there that can be used in planning and execution that can foresee and mitigate problems before they occur. And I think that's what, where we're coming from, especially in the private sector, knowing that we know that business models for running these operations are going to be so critical to the operators themselves, and they can't afford to sit on the ground because we think there's something in the air, or they can't afford to not know how the weather is going to impact them in 4 hours from now, because they've got to give their client assuredness that they are going to get from downtown Manhattan to JFK with 5 hours lead time. So these are the things that, that I think about. And when you look at this chart here, what you see is you're going to see a very complex system with a lot of different moving pieces. And I think the one thread that we need to try to understand through all of this is that consistent, precise, and resolute weather data and information and decision tools are going to be absolutely critical for a well-functioning and non-chaotic airspace. So, Matthias did a great job of pointing out all the local challenges and local effects that are not even really addressed today in any of our products. And part of that is because we've never had a business case or a need as strong as we have right now to be as good as we are. Most of our manned aviation aircraft and the people who fly in them were able to deal with a lot of these bumps and bruises they got along the way when weather data wasn't quite as accurate as we had thought it would be or hoped it would be. But when you don't have aviators on an aircraft, and when you're flying aircraft that are much more weather sensitive, and you're flying them in the boundary layer near buildings and structures that are going to cause turbulence, and you have differential heating, like Matthias pointed out, between the downtown area and the water, these are things that are going to become impactful. And when MIT Lincoln Lab, they conducted this study funded by the FAA, and they demonstrated that this is the report card we have right now on how current available aviation sources rate for UAS needs. And this is something that is going to become more recognized and more impactful to people's business model and revenue as they start trying to schedule more flights, jamming more operations into a smaller envelope, not carefully managing each flight for demonstration and avoiding the weather to make it work, and not flying in places where the weather is always good to demonstrate what they can do. The reality is that reality is going to at some point hit the industry, and we want to do is here as the weather group is we want to get ahead of this problem, and to do that we need operators support, and we need to demonstrate the need for research dollars, and to recognize that the roles of SDSPs, especially these are supplemental data service providers, especially as they're being integrated into the unmanned area traffic management systems, they need to be also integrated into the planning and the ConOps development around all these infrastructure that's being built to support these systems. So, I guess I'm going to take a higher view, but it all starts with observations. And, our models are only as good as how much density of observations, especially in situ and remote sensing observations there are, to understand what the atmosphere is actually trying to tell us it's doing right now. We have so much uncertainty even in just trying to understand what the atmosphere is doing right now, that we prepare our models in a way where we make a lot of assumptions right out of the box. And that initial depiction of what we view as the atmosphere looking like is already an assumption. And there's already errors in that going into a model that is also just a model. And that model also doesn't account for all the aspects of everything that happens that causes weather to occur. I mean, we're getting better at it. Our science is better, much better than it was. And I would almost argue our science is probably ahead of where we are in terms of being able to give enough observations and in our computing power. So computing power, science, and observations make a forecast. And, you know, we need focus on all those areas, especially now when we add the fourth dimension, which are man-made buildings and structures that aren't in our atmospheric models, don't even know they're there. So now we get into the area of computational fluid dynamics and coupling. So TruWeather and we've been out here about 2 years. We're in the New York State test range. We're on several contracts now with the FAA as a sub to do some work in the UTM arena. We're working in the state of Ohio and been hired to help them develop their unmanned aerial system traffic management. We've been out supporting operations. We just completed support for an operation from the islands south of South Korea, where they delivered masks, 8.8 kilometer BVLOS mission. And you know, we're learning a lot as we're out there about the impacts and what kind of data we have and what kind of data we're really going to need to be effective. And I think, you know, the one point I want to make is the weather's never a problem until it's a problem. And so, you know, 90% of the time you may not have a problem. It's only that 10% of the time that you may have a problem, but that's when your world falls apart. And we need to make sure that, you know, we have processes, techniques, procedures, even within the operations world, and better training for them on how to deal with these microclimate problems that pop up that can cause your battery to run out faster, cause you to, you know, have some stability control issues and other things. What we have found is that Part 107 and Part 135, the weather training, and I know this because I built a module for somebody to do the weather training in Part 107, and it's woefully inadequate for the missions that we're training our pilots, you know, asking our pilots to do. And the requirements also for what the weather, what the weather information required for them to fly is also pretty inadequate. And again, this is not anybody's fault. You know, we're trying to grow this community quickly. And for the most part, we cut and pasted manned aviation weather requirements into Part 107 and 135. And so, you know, what we have now is a situation where we need to go in and figure out, you know, what do we really need to do and require, and what are those performance requirements. And then, you know, the challenge that we see is, you know, folks, generally the threats that are capturing people are the things you can't see, right? Like winds aloft, turbulence, icing, thermals, as Matthias was pointing out over the city. You know, if you're flying a light UAS with a wingspan that's a little larger, you know, you're going to get dislodged potentially by some strong updrafts in the summertime. And, you know, how does this impact airspace management, separation, deconfliction? You know, these are things that, you know, as I've been working in the industry, I'm starting to recognize and think about. And because, you know, we're also involved in working with the Swiss U-Space group and also ASTM F-38, and we sit in a lot of the meetings with the UTM service suppliers and others to talk about, you know, what are all the pieces have to come together to have a, you know, a smooth operating ecosystem. And, you know, these are the types of things that I think, you know, we need to be paying attention to make that happen. Matthias, you know, went into a great deal of detail about the City Canyon problem. And I think that, you know, the way I view the problem is, you know, we've got to have something that gets us better intelligence than we have today, which is nothing. We really don't have any operational capabilities that are sustainable and can support large scale operations right now in a city of small UAS and eVTOLs. And we need to, you know, the first step is getting something that allows us to identify hotspots just so we can keep people away from those areas. You know, the second step is to get the sensing and the better information integrated into the science so that we can improve upon that and get, you know, a little bit better handle and understanding of specifically where these areas will reside within the urban area. And then I think finally we need to reach the plateau that Matthias was talking about, which is really getting into understanding how these thermals and eddies are flowing during different parts of the day at different altitudes, and making that, that ultimately would be the system we'd all, are seeking to do. And it's going to require, more sensing, better models, and it's going to require also some machine learning and other techniques. I think it's going to require IoT data sets that are good enough. I think we got to make sure that, we don't get backed into a corner where we think we have to have an ASOS quality observation on every street corner, because that's not going to happen. We've got to keep sensing affordable so that we can encourage and incentivize the private sector to put sensors out there and provide data that the SDSPs can take and use and upgrade their products. And I believe we're looking at a model of fees for UAS operators and eVTOL operators that would come through the UTM service suppliers that go back into the system and help support some of this infrastructure that I don't believe the government's going to be able to do on their own, especially right now with the deficits and the other issues we have on our plate. So what are the urban weather challenges? I think, again, Matthias, outlined it very, very well. So I'm just going to focus on operationally what I think are important to figure out, right? These invisible threats, above ground level and above ground level, the turbulent eddies that can cause stabilization control impacts, Ventura effects, where we have rapid changes in wind speed and direction over very short distances that are caused by buildings and not by the atmosphere. Microburst translation, what happens, if you have a collapsing storm, especially out in the desert areas where, you can have a translation of winds can travel, 10s or 20s or 100 miles and hits an urban canyon and then starts getting all chaotic within that canyon. That's not something that we have the ability today to forecast in our model. We don't even have the ability to hit the microburst forecast without it already either in the process of occurring or some very good tools that say it is going to occur. So these are areas that, microbursts are something that, or any of these are something that can change rapidly. So, one of the things that folks always say to me, pilots say, we just need, these are only 10 or 20-minute flights or half-hour flights. We could, the weather doesn't change that fast. Well, that's probably the case 99.5% of the time. But, there was a snow squall event that went through New York City several months back, and I talked to people who told me that absolutely killed their ability to get chaos under control, moving people around in air. And so, things happen and you got to plan on it and you got to know how you're going to deal with it. It doesn't mean we're going to be able to forecast it all right away or perfectly, but we just got to understand that it is a problem that is going to be something that has to be worked with and mitigated and addressed over time. And we need to plan that into our system so that, over time we get better at it and we can start mitigating those impacts. He's already talked about the subclimate, some subgrid microclimates. And I know that, FAA, once they figure out that unmanned vehicles are flying 10 miles and they're flying through patches of fog that nobody knows is there, they're going to want to know how we're going to improve that capability to give better granular information that people are actually following the flight rules, right, that are required. How do we enforce the flight rules that are required? And then we talked about temperature and, urban heat island. They saw it out in TCL4 out in Reno where the building tops got very hot and they were running into density altitude issues. Again, ambient air temperature is a lot different than building air temperature. When you're only a couple of feet off the ground, that's not ambient air temperature. And so how are we going to understand what those temperatures are and how they're going to change through the day, and how is that going to impact loading and weight and all those things that you got to think about when you're trying to move people and cargo. And so again, talking about cargo and people, the client experience is also a factor in this. You could definitely, these aircraft are going to be built to tolerate a lot. There's no doubt about it. Although I've been told that we're going to have an all-weather aircraft since I joined the Air Force in 1984. And I still haven't seen one yet. But the bottom line is that, you know, these engineering challenges are doable if you have money and you can carry a lot of weight and do things. But it always seems like the business model gets in the way of good engineering sometimes. So we've got to think about, you know, how we're going to impact not just how these aircraft are going to be impacted by the weather themselves and what they can take in terms of airworthiness, but what about putting somebody in it that's going to throw up on the way to the airport? That's not exactly a good client experience, right? So you got to think about things like that. And when I look at Matthias's eddies flying out, you know, coming out of Dallas with a 5 meter per second vertical lift, I know it's not going to be smooth, and you know, people are going to get sick. And you know, if they don't have a good client experience, they're not going to come back, right? So these are things you got to think about in a business, right? And also the decision about how far in advance do you need this data, because most folks that are going to be moving people on demand, they're going to need to have a pretty clear understanding 5 hours in advance if those clients are going to show up, they're going to get them to that airport on time. And so you need to have lead time. This is not just about real-time weather information. This is about a business that needs to have information that will actually dictate whether or not they're going to be able to meet that client contract that they have. And, you know, I talked a little bit about airport METAR temperatures versus, you know, downtown. Big difference. You know, you can fly from Manhattan to over the Sheepshead Bay and then over to JFK in the summer, and you can go through like 3 major climatic zones, and temperatures will vary, you know, could vary anywhere from 70 degrees to 120 downtown on the skin, right? Because if you have a little, you know, you're over Sheepshead Bay, you have a little sea breeze that hasn't penetrated all the way into New York City because you have a strong southwest flow, but it's enough to get over Sheepshead Bay, and that water temperature is 68 degrees, you're going to have a lot of different temperatures you're dealing with along that route. And then, of course, no human pilot. And it's really difficult. I mean, how much the human pilot does and the inferences it has and the processing it's doing, that person's doing to, you know, deal with all the weather inadequacies we have in accuracy, precision, and measurements is probably not well understood. And it's going to be really hard to replicate that in machine learning for a long time. And I just, again, if there's no pilot on that plane, you're losing a level of capability, right, to deal with these events. And that's something, again, research we should be looking at. And then data latency. We talked earlier about, you know, it's only a 20-minute flight, but, you know, outflow boundaries coming in from thunderstorms that occur 20 miles away, which don't ever even come near your route of flight, pop-up showers, pop-up thunderstorms, localized ceiling and fog, you know, microbursts. You know, these are things that latency is going to be important to measure and get to a decision. And I think, you know, these are some of the things we need to look at also. So, you know, taking on the most difficult challenge first, I think, you know, is really this idea of the cityscape and how we're going to, you know, work through this urban environment problem. And I think, you know, we need to get a project going in a proof of concept and find a city that's willing to play, that says, you know, what can we measure? What can we do to measure and understand the scope of the problem? How do we decide where to put sensors in a city, right? I mean, again, budgets are limited, you know. I mean, even if you can get a municipality to agree, hey, I'll pay for some sensors as part of my smart city initiative. You know, if you ask me or another meteorologist, so how many do you need? I'd say I want one at every street corner. I want one at, you know, at 10 feet. I want one at 200 feet on every building and around in the middle of the streets and all that, right? That's not going to happen, right? So the question becomes, how do you figure out, you know, where do you start with a sensor coverage that's going to give you a maximum bang for the buck at the lowest cost, but give you some intelligence much better than we have today, you know? And that's kind of like the 80-20 rule in my mind. So it does require a framework, and it requires that we got to start thinking not just about the ultimate solution, but we got to start thinking about intermediary steps. You know, crawl, walk, run. I know it's an old cliche, but it really means something. You know, how do we start a framework and start biting off some of this huge elephant that we have to work through, and doing it in coordinated steps so that we can begin learning and begin solving some problems, even if it's not the perfect solution. And, you know, if we can find a way to optimally place sensors in a city, any city, and everyone's going to be different because they all have different, you know, structures and footprints, you know, we can start to, you know, build up a database. We can start doing some coupled, you know, high resolution atmospheric and CFD modeling. We can begin learning, taking the data and improving the system. And, you know, we could start slowly, you know, developing a better solution. This is not something that's going to get solved in even 20 years. This is a long-term effort that's going to probably never be perfect enough in my lifetime, and maybe not even in some of the younger folks' lifetime that are sitting in this webinar, but we have to start somewhere, right? And then of course there's hurdles, right, to all of this, and figuring out how do we begin to sense cities and sense areas. And it starts with, you know, we need communication. And I think the bandwidth for communication is something that is doable if we're not vying for all the communication for all the private, civilians. But there's some of these networks now that are building have dedicated communication bands just for the government services. And I think, you know, we got to make sure that weather data becomes mission critical and mission essential, and that it's recognized as an important component of emergency management and other systems. And then computer processing, of course, is always going to be the long pole in the tent. The challenge is how much can we distribute this computer processing? How much could be edge computing? How much could be products that are developed locally and sent back out locally without going all the way back to the cloud and just sending back what you need and processing what you need? And we got to think about, you know, this is a whole architecture for weather to think about how do we want to, you know, lay out this IT computer processing infrastructure using modern techniques that are being used within the smart city realm. And then, you know, smart in situ sensors, you know, what kind of sensors do we need? You know, how good do they have to be? What's good enough? How do, you know, where is the placement? So these are the things that, you know, we got to work towards, but we also have to make sure that it's affordable and that there's a way to amortize these costs across all users, because the government's not going to pay the bill for it. And the only way you're going to do that is by setting up a public-private partnership approach where there are fees involved and money's flowing back to the sensor owners and others in some way, shape, or form to offset those costs. So you know, I've been, again, working in this for about 2 years, and I've been sitting in the ASTM F38 group for a while, and we managed to get them to recognize that we do need a weather standards group, and they're calling it supplemental data service provider weather standards group. It's important that this group work with the private sector and with the government entities, and we have FAA representatives on this group. Marilyn, who's going to speak next, is on it. We have major companies like Amazon, Airbus, UPS, Uber on it, and we have UTM providers on it. And the goal is to develop, you know, a framework first. We gotta get approval for our tour in terms of reference, which we're working on right now. And that the goal is find the sweet spot where we can drive innovation and not just cut and paste what we've been doing for the last 50 years. Think outside the box a little bit about what's good enough. Come up with those performance standards, maybe based on risk, you know, maybe based on aircraft type, maybe risk profiles, and get those working and get a first set or an initial set of standards that isn't going to solve world hunger, but is going to give us something that's better than what we have today and is also executable. So we don't want standards that are going to be based on science and technology that we're not going to be able to deliver for the next 10 or 15 years. It has to be something that's executable, but realizing that it's going to also evolve and that the first draft tour and the first standards are not going to be the last standards. It's going to be an evolutionary process. And that everything is focused on quality control and quality assurance. We don't have to necessarily certify systems like we have with ASOS. We need to certify data. We need to look at the data and look at, how good the data is and what's good enough, and then potentially use certain data sets for certain decisions based on the quality of that data. And these are, there's just a lot of work to be done here, and there's going to be a lot of folks are welcome to join this group if they would like. You could see my email address on the bottom, and we welcome you. So that's what I have today, Rex, and everyone out there. Thank you for the time today, and I really do again appreciate the smart people that are on this webinar today also presenting. I see a lot of alignment in thinking now, a lot of advancement over the last year in maturing, and now we can start looking at how we can work together to get the maximum effect of all these capabilities and not pull against each other, but work together. Thank you.
Don, thank you very much. Greatly appreciate your insight on this new and burgeoning aviation arena and how weather will need to play such a critical role. Our fourth and final speaker today is Miss Marilyn Pearson. Marilyn is a career aviator with 4 decades of experience, including piloting gliders, single and multi-engine aircraft, rotorcraft, as a turbojet captain in international operations. Marilyn has been an aviation safety inspector with the FAA for nearly 23 years, serving as a national resource pilot and as a train the trainer for new initiatives and procedures in safety management systems and safety resources management. Marilyn currently serves as an unmanned aircraft specialist with the FAA's General Aviation and Commercial Division, AFS 800, providing expertise in the rulemaking process for Part 107. Marilyn serves as a co-chair for a weather products and services community of interest, with emphasis on closing weather gaps in low-level boundary layers operations and developing policy and guidance to meet weather needs for stakeholders. Please welcome Miss Marilyn Pearson.
Thank you very much, and thank you all for inviting me to the Vertical Flight Society to present today. And I'm very happy to share this opportunity with the professionals that have spoken before me. I've had a day and a half to present for you, so I will try to do my best. I'm going to give you a different perspective, an operational perspective from the policy and regulatory priorities that we have related to unmanned aerial systems. I'm not a meteorologist. I am a career pilot, so I work within the FAA developing policy guidance and on many regulatory groups. We are currently working on operations over people, the remote ID, and we're going to be working closely to integrate with UAM, UTM. So currently the standards for manned flight, when we talk about the approved weather sources, we're talking about approved sources that we use in the 14 CFR, the Code of Federal Regulations, the requirements for the certificate holders, the Part 135 on demands, and the Part 121 air transport. We talk about having National Weather Service as one of the approved providers, a source that would be approved by the National Weather Service or by the administrator, and other sources. Some of these other sources may or may not meet specific regulatory requirements. So this is what we expect the manned aircraft operators to use. The commercial information providers have prepackaged or repackaged weather information. They retransmit the National Weather Service. When I say it may not conform to the National Weather Service standards. It may have a latency and it may have other variants. The eWinds gather and evaluate, disseminate weather, weather forecasts, reports. They are done by trained and qualified meteorologists or dispatchers. Flight movement forecast, these are used by a dispatcher for an air transport category operator, and these are done with the approval for specific operations. Again, more of the standards that we have for manned aviation weather. We have aviation meteorologists, and several folks have spoken to you already who are aviation meteorologists. They hold a degree or several degrees. They could be employed by a certificate holder. They successfully complete training and recurrent training. We have dispatchers, airline dispatchers, for example. They can issue FMS. They have the authority, and they're trained and qualified as well. PIREPs are a really critical portion of our aviation reporting. These can be done by the small aircraft operators, the general aviation operators who might be flying something like a Cessna 172 or the Airbus. And when you're using a PIREP, you need to understand the difference between what's being reported by a small aircraft, a GA aircraft, or by an airline, so that you understand what the visibility or the circumstances would be relating to your particular operation. And this is also something that's voluntary, and we are currently trying to encourage more PIREPs. They're more valuable when we prepare weather forecasting. They are helpful in adverse weather, and they're also helpful when the weather is not as serious as it's been predicted. So we encourage PIREPs for all different weather conditions that can be broadcast en route by the pilot to the ATC facility, or they can be done on the ground after the flight. So I think you're already starting to see some of the differences between manned and unmanned and what the requirements might be. Here we are in the Part 107, which is the UAS, small UAS, below 55-pound realm. The requirements in this regulation are the minimum flight visibility, which is 3 statute miles, and distance from clouds, 500 feet below and 2,000 feet horizontally. And that is really the only weather requirement or restriction that we have for unmanned aerial vehicles from a regulatory perspective. You've probably seen this already. This is the MIT Lincoln Lab study where we have been told many times over that the current products that we have, the current approved products, are not good enough for UAS and UTM problems. So what's good enough? Well, we have the gold standard of the approved weather, and we're trying to determine what would the silver standard be? What is good enough? We have current published weather data standards that are done by NOAA, WMO, ICAO, others. We know there are gaps in the low altitude and the boundary layer airspace weather nowcasting and forecasting. In fact, in some cases, it just simply doesn't exist. So we need to improve our awareness for UAS. You've heard from several of the speakers about winds and turbulence. We're also concerned about precipitation, icing, and thermals. With regard to some of the operations that are approved, and we have nearly 70 beyond visual line of sight waivers for operators right now, with no specific weather standards in the special provisions that are attached to these waivers. So in other words, we have beyond visual line of sight operations that may or may not have a visual observer, and they have no specific weather requirements. So we don't know what they're flying into, and they probably don't know what they're flying into either. So this is a problem. You may have perfect weather at the beginning of the flight. Somewhere en route, you may encounter precipitation, and the precipitation may be in the form of rain or freezing drizzle or snow. But any of that may adhere to a small unmanned aerial vehicle, to the airframe or the propellers is going to be quite critical. We also have an issue here with the latency of information that we have in current weather. No published or in development standards. We have a critical problem with developing regulations because the 2018 Reauthorization Act said that we cannot make current regulations more restrictive. So the current regulations for Part 107 operations, and even the Part 91 or the 135 operations that we see now for unmanned vehicles, don't have sufficient weather requirements. So we're going to have to determine what a policy might be, or perhaps on a case-by-case basis. How can we improve some of the gaps that we have? Some of these products are possibilities. Drones themselves that have sensors on them for wind, speed, direction, temperature, dew point, and so forth. The GOES satellites, perhaps. This is one specific company that has developed a drone with sensors that have the capacity to give an entire suite of weather information. It's one possible solution to a problem. The FAA is developing weather cameras and verified weather observation systems. And these products are now fully in use in Alaska. They've just become implemented in Colorado, and we do intend to implement them in the lower 48 in the CONUS. These replace AWOS systems where they are not existent. And we know that in the lower 48 that we're dependent on weather that comes from airports. And we also know that unmanned vehicles don't always operate anywhere near an airport. So current weather is not appropriate for their operation. And these AWOS, VWOS systems will replace that capability. They have 360-degree cameras with textual imaging. The cameras have pan, tilt, and zoom capability that can be operated by the operator. They are night vision enhanced. They're similar to a long-line METAR. Each has 4 camera bodies within it and 4 camera lenses in each. So there is sufficient redundancy and accuracy, and they are present weather sensors. So this is one possibility that would serve the boundary layer community or the unmanned community. The problem with this is the cost being over $100,000 each. Some of the weather options that may be available to unmanned pilots, the METARs, TAFs, SIGMETs, AirMets, PIRETs, SIGCHARTs, all of these services are available, but they may not be appropriate. The HEMS tool that we heard about previously is an excellent product, but it may not be granular enough. It may not serve the unmanned community appropriately. Operators of unmanned systems, perhaps they could become qualified weather observers and serve their unique operation appropriately. And the risk-based regulatory framework, we do need to address and close the gaps between the regulations and the reality of what's needed in the unmanned system. And to do that, we do need private sector involvement. And I believe Don spoke to that pretty eloquently. The FAA's next-gen aviation weather develops suites of available weather products, and they're expanding. We do have funding to do some work in the low level in collaboration with some of our partners within and our stakeholders. We're developing new weather products and types. The research programs that are going on right now are also looking toward the future for unmanned and low-level weather. And what is next? Well, these are the questions that we need to answer. We need to answer them either within the FAA or in collaboration with our stakeholders. Do we need to have weather that is certified or approved, or do we have the good enough, which would be a silver standard? Do we have government weather services that can close the gaps? And many areas, the answer to that is no. Could METARs be expanded beyond the current 5 nautical mile area? Probably not. Will operators enlist weather observers who could become certified? Maybe. But a problem exists here in that we don't have regulations that require the operators to have specific weather forecasts or nowcasts. And I can't see from my perspective that the operators are going to finance their own weather observation systems unless there's a requirement to do that. So that could become problematic. We need to partner, obviously, with our stakeholders. The Part 135 certifications, are they comprehensive enough where weather's concerned? Part 135 are the on-demand or the package carrying operations now, which eventually will expand to people carrying, maybe not within my career at the FAA, but at some point in the future. We don't have e-winds for the boundary area weather yet. Can we use performance-based standards for weather? We are doing that when we evaluate exemptions, and that's the over 55-pound operations, and when we evaluate the beyond visual line of sight requests. We look at what the proposal is. However, our standards for weather are a bit remiss in that we accept the operator's statement that they will remain VMC. And we really don't ask them how they propose to remain VMC if they're operating beyond their own line of sight. Will we have UAS operators providing PIREPs? Well, maybe, and maybe it'll be called something else, maybe UREPs. And will that provide information for wider use? Could it be automatically reported by the drone? Maybe. Those are all possibilities. As I said previously, the FAA can't develop policy that's more restrictive than our regulations. That was part of our Reauthorization Act in October of 2018. And from the end user perspective, many of you on the phone, what are your needs? And how are you willing to collaborate with the FAA or with your government entities to close those gaps and fill the needs? One of the largest problems that we have from an FAA perspective is how do we educate non-aviators? Many of the unmanned operations are companies and individuals who do not have pilot certification in manned aircraft. And there's a gap in the knowledge. Again, one of the largest problems that we see from the private pilot through to the airline transport pilot is the written exams require a certain amount of weather questions to be answered. And it is possible in any of these exams, written exams, that you can fail all of the weather questions and still pass the exam with a 70%, which does not lead for confidence in operation in variable weather conditions. Can we leverage other companies, individuals, other governmental entities? Will the GOES satellite provide information that will be satisfactory. We have the weather cameras and the validated weather service observation systems. Are those going to be good enough? And could those possibly be reproduced maybe by stakeholders in a more financially compatible area where the stakeholders could develop perhaps something along the nature of these weather cameras, but maybe not so sophisticated. It might serve their purpose adequately and from a much more economically feasible means rather than spending the 100,000 plus for these weather systems. So these are some of the questions that we need to answer within the FAA, and we look forward to working with our stakeholders. If you have questions, there is a portal, I guess, for questions. And thank you all for listening, and thank you to the Vertical Flight Society for inviting me.
Marilyn, thank you so much. Greatly appreciate everything. In lieu of the fact that we don't have a lot of time, I will go ahead and suspend the Q&A for today. We have gotten everyone's questions, and what we'll do is send that out to our experts and get the response back from them, and we'll post that along with all the presentations and the recording of today's session on the Vertical Flight Society's website. A special thank you to today's speakers as well as our sponsor, Deolite, and thank you to everyone for joining us today. We hope that you found this discussion useful and insightful. Be sure to visit our website to see the entire Urban Air Mobility Infrastructure webinar series, and be on the lookout for information for our next face-to-face workshop, which will be, right now, it looks like September in this fall. So with that, I bid you all a farewell. Be safe, be healthy, until next time. Thank you.